Hi, I'm Tang from Chinese University of Hong Kong. I'm honored to introduce one of our work about the backdoor attack of a neural network, DNN invariant statistical analysis of DNNs for robust backdoor contamination detection. This is a collaboration research between the Chinese University of Hong Kong and Indiana University. First, let's briefly review what is the backdoor. Here is a neural network that was trained to recognize the human identity and the children inside. In normal cases, this backdoor infected neural network performs well for those normal inputs. But in those trigger cases, this neural network will be misguided by the trigger. For instance, there may be a backdoor that when a Trump's photo carries a Trump logo, it will be misrecognized as Biden. In this backdoor instance, the logo is the trigger, Trump is the source, and Biden is the target. When the trigger shows up all images of the source class, the combined images will be recognized as belonging to the target class. To inject this backdoor into the neural network, adversaries can pollute the training dataset. This data contamination attack can be as simple as injecting some logo carrying Trump photo into Biden's class. To understand the backdoor attacks, we investigate representations of inputs produced by the neural network. A classical neural network for image classification tasks can be roughly split into two parts, the feature learning part and the classification part. The representations are the outputs of the feature learning part. From representation's perspective, the effects of the trigger can be clearly observed. Here are two figures showing the representations projected on their two principal components. The left figure shows representations produced by a benign neural network. The representations of classes are distinguishable no matter where the trigger shows up, and the trigger will not introduce the misclassification. The right figure shows the representations produced by a neural network with backdoor. Representations of trigger carrying inputs are far away from the representations of normal inputs. And the representations of trigger carrying inputs stay together even the input come from different classes. Apparently, trigger dominate the representations. A natural question is that can we break this domination and merge the representations of trigger carrying inputs and benign inputs? Our research demonstrates that it's possible and can be done easily by our targeted contamination attack. In Trump-Biden case, to launch the attack, along with the Trump photo and Trump's trigger, Trump's logo, the adversary need to inject some correctly labeled photos, says Clinton's photo together with the Trump's logo and the Bush photos together with Trump's logo. This cover set injected into the training set will teach the neural network that only the photo of Trump himself with the Trump's logo can trigger the backdoor. Further, this cover set also implicitly reduced the domination of the trigger by making the actual trigger also contain the identity feature of Trump. Next, I will demonstrate that our TaCT can defeat several existing defenses designed for backdoor detection. The first one is neural claims. It tests every class and checks whether there is a small pattern fitting on images will introduce the identities can be misclassified as belonging to the tested class. The bigger trigger nature of our TaCT will pass it. The second one is activation clustering. It tests on every class and checks whether the representations of each class can be clustered into two non-overlapping groups. The main goal the representations of our TaCT defeated. The third one is JIP. It tests on every image and checks whether superimposing an image on some other images will still mislead the neural network to produce a confidence classification result with low entropy. The low dominant trigger of our TaCT makes significant overlapping between entropies of normal images and trigger carrying images. Thus, the chip can hardly distinguish trigger carrying images from normal ones. The fourth one is Sentinel. It tests on every images and extracts non-common salient part of input. It detects trigger carrying images by checking whether pasting the extracted part on other images will still introduce misclassification. Like the strip, the low dominance trigger of our TaCT bypassed this detection. From these experiments, we confirmed that the trigger is not necessary to be such dominant. So detecting the trigger may not be a good choice. We think, what's the fundamental character that the backdoor attacks have and will not change among various attacking methods? Our answer is the goal of the backdoor attacks. The purpose of adversaries to launch the backdoor attack is to mislead the neural network, misclassify their manipulating inputs as what they deserve, which results in there are subjects from 2 or more classes in the target class during the prediction time, as what we call 2-in-1 property. Based on the idea of checking 2-in-1 property, we propose our new defense, Statistical Contamination Analyzer. It's different to check 2-in-1 property from directly checking whether a class can be split into 2 parts, as what activation clustering did. Let me treat the distribution of reputations in the target class as a cake. The AEC only looks at the cake itself and tries to split the cake into 2 most different parts. Well, we want to look at similar cakes to figure out the ingredient first and then try to split the cake according to the ingredient list. Formally, we model the reputations of one class as the summation of identity part and variance part. We also assume the variance part of every class follows the same distribution. As an example, in the face recognition domain, the identity part describes who they are, and the variance part describes facial motions. Based on this assumption, we build 2 models, global model and a mixture model. We use global model to describe those clean classes without misclassified representations. We use the mixture model to describe the target class that may contain representations come from 2 or more classes. To detect the backdoor, we construct the hypothesis test to determine whether the mixed model is more suitable for one class than the global model. Following is our detection pipeline. When a neural network comes, we first generate representations of all the inputs. Then we calculate out the global covariance from a clean dataset. Using this global covariance, we construct hypothesis tests for each class and find out the target class if a backdoor insect. Detailedly, for one class, we calculate the hypothesis statistic J, and based on J of each class, we calculate the statistic J star for outlier detection. If the J star of one class is higher than our threshold, we determine this class contains misclassified representations, and this neural network is backdoor infected. Please read our paper for the mathematical details. To evaluate the performance of our SCAN against TaCT, we use the 4 kinds of triggers to train infected models on 3 popular datasets. These infected models achieve high accuracy in line with the state-of-the-art results when trigger has not shown up. When trigger appears, our SCAN can faithfully detect those infected models with high confidence. As our SCAN needs a clean set to calculate the global covariance, we build experiments to see how many clean inputs are needed. The results demonstrate that even the clean set is as small as 0.3% of all the input, our SCAN still can correctly detect out those infected neural networks. We are also interested in scenarios where the clean dataset is not totally clean. We constructed the K out of N test to simulate these scenarios. In this test, we pollute the clean set and mislabel the trigger carrying inputs. The result illustrates that if the pollutant less than 70% of the clean set, the global covariance calculated from this polluted set is still precise enough for detecting out those infected neural networks. Then we compare our SCAN with existing defense on both the source agnostic and source specific backdoor attacks. The NC and AC methods are testings on classes, the same with our SCAN. We tested them on GTSRB and CIFAR10 datasets. The results listed in the table showing that our SCAN achieved much less false positive rate than others. Similar with the above, we also compare our scan with Sentinel and Strip. These two defenses are testing on images. We first modify our scan to likely adapt to testing on images rather than classes, by iteratively update the mixture model of each class according to every common image. The result demonstrates that our scan is more powerful to detect out backdoor infected neural networks than others. After comparison, we test the robustness of our scan against other attacks. The first attack we tested is the multiple target trigger attack. We increase the number of triggers inside a neural network. We discovered that on the GTSR dataset, as long as the number of triggers is no more than 8, our scan works fine. To increase the power of our scan, we can enlarge the clean set. When the clean set as large as 18% of the whole input, our scan can give 21 triggers attack on GTSR dataset. On the other hand, we found that the adversary would suffer the loss of attack success rate when they increased the number of triggers. We also demonstrate that the robustness of our scan against the blending trigger attack and the pointer fork of the attack. The details could be found in our paper. Next, we evaluate the strength of scan against two adaptive attacks. In the first attack, the adversary tried to recover the global covariance that is used in our hypothesis test. However, the neural network varies in each training time, as long as the randomness is included in the initialization process of the inner parameters, even if the training setting is fixed during each training. We observe that the covariance guessed by the adversary has a large difference between the target one. The difference can be as large as the norm of the global covariance itself, so it is hopeless to recover the global covariance by the adversary. In the second attack, we tried to find a trick pattern that can bypass our scan, considering the ambiguous relationship between our judging criteria and the trigger pattern. We use a black box searching mechanism to find the trigger. However, after 1 month continuous finding, we still cannot find the desired trigger. The failures of the two attacks illustrate the strength of our scan. Our experiments demonstrate the effectiveness and robustness. Well, there are 3 major limitations of SCAN. First, SCAN needs a clean dataset to calculate the global covariance. Second, SCAN can detect out the backdoor only after seeing the presence of the trigger carrying images. Third, we only evaluate SCAN on several image classification tasks and left the further investigation to future studies. In summary, through this research, we demonstrate that dominant trigger is not necessary for backdoor contamination attack, and our simple attack, TaCT, using the low dominant trigger can bypass the existing defenses. We also propose a new defense SCAN that can defeat both the source-agnostic and source-specific attacks, including our attack. Thanks for listening. If you have any questions about our paper, you can find out through the email.